All right, let's get started. Today, we're going to peel back the layers on the language that computers speak. We're going to demystify these number systems that literally power our digital world, and we're going to translate that complex code of ones and zeros into something that makes perfect sense. Let's jump right in. You know, I love this quote. It's funny, right? But it actually sets the perfect tone for today. We totally take our own way of counting for granted, but as we're about to see, computers have a completely different and way simpler way of looking at numbers. So here's our game plan. We'll start by looking at the difference between the real world and the computer world. Then we'll dig into how computers developed their own simple language, why that language is a total headache for us humans, and the brilliant shorthand we invented to deal with it. We'll even learn how to speak a little computer ourselves before we wrap it all up. Okay, first step, let's tackle a really fundamental idea, the difference between analog and digital. This is the absolute key to understanding why computers have to work the way they do. Think of it like this. The analog world is smooth, it's continuous. The mercury in an old-school thermometer can land on any possible temperature, right down to an infinite number of decimal places. But the digital world, it's made of separate, discrete steps, kind of like the beads on an abacus. You can't have half a bead, right? A bead is either here or it's there. This makes digital way less ambiguous, but it means it can't represent all those infinite values in between. And that's the core trade-off. So if computers are digital, they need a number system that's also made of discrete steps. And when you're talking about an electronic circuit, what are the simplest possible steps you can have? Well, it's just on and off. So how in the world do you build an entire universe of information from just that? And the answer is binary. It's a base 2 number system, which just means it only uses 2 symbols, 0 and 1. In a computer circuit, off is a 0 and on is a 1. It's that simple. And this incredibly reliable system is the foundation of all modern computing. Now, what's so cool about this is that binary uses place value, just like the decimal system you use every single day. But instead of powers of 10, the ones place, the tens place, the hundreds place, binary uses powers of 2. So you have the ones place, the twos place, the fours place, the eights place, and on and on. If you look at the example here, the binary number 11010 breaks down into a 16 plus an 8 plus a 2, which all adds up to 26 in our system. So binary is just perfect for machines. It's elegant, it's efficient, but for the human engineers and programmers who have to actually work with these things, well, it creates a massive new problem. And this slide really says it all, doesn't it? Just look at the number 20. In decimal, it's 2 simple digits. In binary, it's this 5-digit string of ones and zeros. Now just imagine trying to read or write a number in the thousands or millions. It is incredibly difficult for our human brains to process. And believe me, this isn't just a theoretical problem. Some of the very first computers, like the famous ENIAC, actually tried to get around this. They built a more complex system based on our familiar decimal numbers just to keep them shorter. But it turned out to be a total clunker, unbelievably inefficient for the hardware. The simple beauty of on and off won out, and that's why virtually all digital computers since have been designed as purely binary machines. So we've got a language that's perfect for computers, but absolutely terrible for humans. What's the solution? Well, engineers came up with this really brilliant compromise, a kind of shorthand to make binary manageable. Meet hexadecimal, or just hex for short. It's a base 16 system. That means it uses our regular 10 digits, 0 through 9, and then it just adds the letters A through F to get to 16 symbols. Now, the most important thing to get here is that its purpose is not to replace binary. It's just a compact, human-friendly way to represent it. So, why base 16? What's so special about that number? Well, here's the magic trick. 16 is 2 to the power of 4. And what that means is that any group of 4 binary digits, what we call bits, can be represented by exactly 1 hexadecimal digit. It's this perfect, clean grouping that makes hexadecimal so essential in computer science. You see it everywhere, from the color codes on websites to the memory addresses that help your computer find data. Let's just watch this in action. First, you take a big, long binary string, like the one you see here. Next, you just break it up into little groups of 4. Now you convert each group. Take that first one, 1010. That's 10 in decimal, which is the letter A in hex. The next group, 1111, is 15, or F. You just follow that process, and that really intimidating string of ones and zeros becomes the short, readable hex number AF5C. Much better, right? So now that we get the why behind these systems, let's roll up our sleeves and learn a practical skill: how to translate a number from our world into the computer's native language. We're going to use a really simple and reliable process called the repeated division method. And our goal here is to convert the regular old decimal number 87 into its binary form. Okay, let's just walk through this slide together. We start with our number, 87. As you can see, we divide it by 2. That gives us 43.5. That 0.5 tells us we have a remainder of 1, so we write that down. That's our very first binary digit. Then we take the whole number part, 43, and we just do it again. 43 divided by 2 is 21.5, so we have another remainder of 1. You just keep doing this, dividing the whole number by 2 and recording the remainder every single time until you get all the way down to 0. And now for the final step. You take all those remainders you recorded and you just read them from the bottom up. And there it is. The decimal number 87 is 1010111 in binary. So we've gotten into the nuts and bolts, but let's just take a step back and appreciate how profound this all really is. So what are the big takeaways? First, our entire digital world is built on the simplest possible distinction: on or off, 1 or 0. Second, while binary is perfect for machines, it's a total nightmare for us humans. Third, hexadecimal acts as that friendly bridge, a compact shorthand for binary. And finally, with simple methods like the one we just used, anyone can learn to translate between these different languages.
It really makes you think, doesn't it? Everything you're watching this on right now, every app you use, every photo you take, it all just boils down to ones and zeros. It's a powerful reminder that the most revolutionary technologies are so often built on the simplest of ideas. It kind of leaves me wondering, what's the next simple concept that's going to redefine our world?